Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe. All right, lecture 22 is on combinatorics, which is a really fancy way of talking about how many different ways there are to count certain events up. I've already actually done a video on this on my Prodigy Physics channel, and I'm going to use that in this lecture, but then we'll pause from time to time and work some problems along the way, because it's more of a edutainment video and not so much an educational video. So we'll kind of reinforce it with some problems in the lecture here today. So let's go ahead and begin. Welcome to our exploration of counting. Today we're diving into the fascinating world of combinatorics, where we figure out the number of ways specific events can happen. This isn't the kind of counting that you might teach in kindergarten. It's much more intriguing. Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Let's start with something sweet. Imagine that you are at an ice cream shop. How many different 2-scoop ice cream cones can you make using just 2 flavors? We'll tackle this tasty question shortly. Next, consider a delivery truck navigating the city. How many different routes can the driver take? And what if the route includes a mandatory lunch break at a popular spot on the corner of 5th and Broad? This scenario adds complexity and opens up an array of possibilities. Moving beyond desserts and delivery routes, the principles of counting are crucial in probability, much akin to highbrow fortune telling. For example, tossing a coin twice yields 4 possibilities: heads heads, heads tails, tails heads, or tails tails. What are the chances both tosses land on heads? With one favorable outcome out of 4, the probability is 25%. While probability features in games and predictions, it also plays a vital role in physics, from statistical mechanics to quantum mechanics. However, today we will be focusing purely on counting, starting with the basics. Consider Sophia, who owns 3 shirts and 2 skirts. How many outfits can she create? You might initially think 5, since 3 plus 2 is equal to 5. This would be correct if she were choosing between 3 identical blue shirts and 2 identical white shirts, because she can only wear 1 shirt at a time, and therefore has 3 plus 2 equals 5 choices. This result is called the principle of addition in combinatorics. Since shirts and skirts are chosen independently, the total number of outfit combinations Sophia can create is actually greater than what you might initially think. For illustration, let's consider her wardrobe. She has 3 shirts, 1 green, 1 pink, and 1 teal. She also owns 2 skirts, 1 yellow and 1 blue. Starting with the blue skirt, Sophia can match it with either the green, pink, or teal shirt, resulting in 3 unique outfits. But this is just the beginning. Each additional skirt she owns can also be matched with any of the 3 shirts, multiplying her options. With just 2 skirts, this already gives her 6 possible outfits. This scenario perfectly demonstrates the principle of multiplication in combinatorics. We can expand the possibilities further. Imagine adding another item, like this awesome camouflage shirt. Okay, so we'll pause it there and reflect on this addition and multiplication principle. Well, actually, we're going to look at the multiplication principle. So imagine that we had a delivery truck that had to go between point A and point C, but had to pass through point B. And let's say that there were 1, 2, 3, 4 routes to get to B, but only 2 routes to get from B to C. How many possible routes are there for this delivery truck? Well, 1, 2, 3, 4 on A to B, and 1, 2 going from B to C. So the number of routes there are total, we use the multiplication principle. So 4 times 2 equals 8 routes. So let me give you one to try. So in your problem, we have 3 routes from A to B and 4 routes from B to C. So go ahead and pause the video, calculate the number of routes, come back when you have your answer. Okay, well, we've got 3 routes from A to B and 4 routes from B to C. So there are 3 times 4 total routes, or 12 delivery routes. So we'll go ahead and continue the video from here. When we delve into the question of how many, we encounter different methods of counting, each with unique rules and outcomes. Today we'll explore these through the universally loved medium of ice cream. First up, consider the scenario where order matters and repetition is allowed. Imagine creating an ice cream with multiple scoops. With 2 flavor combinations, chocolate and vanilla, and 2 scoops, how many different combinations can you concoct? If you choose just 1 scoop, the answer is simple. It's either a scoop of chocolate or a scoop of vanilla. But with 2 scoops, the permutations increase to 4. A scoop of chocolate, followed by a scoop of vanilla. A scoop of vanilla, followed by a scoop of chocolate. 2 scoops of vanilla or 2 scoops of chocolate. Because with a cone, you can only eat from the top, so order matters. Some people prefer to eat one before the other. That's why I've chosen ice cream cones to represent situations where order matters in counting. Next, let's consider bowls of ice cream where order does not matter, but repetition is still allowed. Here, you're not concerned with the sequence of scoops. Whether you scoop a scoop of chocolate or a scoop of vanilla first, it doesn't matter once it's in the bowl. With the same 2 flavors as before, chocolate and vanilla, the possibilities reduce to just 3. A bowl with 2 scoops of vanilla, a bowl with 2 scoops of chocolate, or a bowl with 1 scoop of each. The arrangement of scoops in a bowl can be rearranged by simply rotating your bowl or moving your spoon somewhere else. Order is irrelevant when it comes to ice cream in a bowl. Moving to scenarios where repetition is not allowed changes the game. If order still matters, you end up with 2 distinct cones, vanilla chocolate or chocolate vanilla. However, if order doesn't matter, you're left with just 1 possible combination, a single scoop of each flavor. We can organize these 4 cases into a table of 4 quadrants. On the horizontal axis, we consider 2 cases where order matters or not. On the vertical axis, we consider the 2 cases where repetition is allowed or not. The upper left quadrant where order matters and repetition is allowed will hold the 4 unrestricted 2-scoop ice cream cones. By unrestricted, I mean there is no restriction on repeated flavors. 2 scoops of chocolate or 2 scoops of vanilla is allowed. The lower left quadrant where order matters but repetition is not allowed will hold the 2 unique flavored 2-scoop ice cream cones. By unique flavored, I mean that each scoop must be a different flavor. No chocolate chocolate or vanilla vanilla cones here. The upper and lower right quadrants of our table will hold bowls of ice cream, since these are the cases where the order does not matter. In the upper right quadrant, we will place the 3 unrestricted 2-scoop bowls, and in the lower right quadrant, we will place the single unique flavored 2-scoop bowl. These examples might seem straightforward with just 2 scoops and 2 flavors. Okay, so I've drawn the counting matrix that I gave you in the lecture, or in the video rather. So repetition matters is the vertical axis here. So this is repetition matters yes, repetition matters no. Whereas order matters, the left-hand column yes, because an ice cream cone, the way you eat it, order matters. But on the right, they're the ice cream bowls. That's where order does not matter, okay? So let's have a look at one of these configurations. Let's think about what would we have if we had 3 scoops and 3 flavors. So 3 scoops and 3 flavors. And let's do it for the ice cream cone. So this is where we're going to allow for repetition. So you can have repeated flavors in it. So the first thing we would note is that we could have, just 1 flavor. For example, chocolate, 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 vanilla, 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 or strawberry, strawberry, strawberry. For 2 flavors, we could have, for example, chocolate, chocolate, strawberry, 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 chocolate, or vanilla, vanilla, strawberry. But I could, of course, because the order matters, there's another possibility where we could have the chocolate, then the strawberry, then the chocolate, or the strawberry, then the chocolate, then the strawberry, or the vanilla, the strawberry, and then the vanilla. These would be different cones. We could also have chocolate, chocolate, vanilla instead of chocolate, chocolate, strawberry, 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 vanilla instead of strawberry, strawberry, chocolate, or vanilla, vanilla, and chocolate instead of vanilla, vanilla, strawberry. And these two we could permute again by simply moving the vanilla to the middle of the cone. So it'd be chocolate, vanilla, chocolate, strawberry, vanilla, strawberry, vanilla, chocolate, vanilla. Or we could start it with a single flavor, chocolate, strawberry, 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 chocolate, chocolate, or vanilla, strawberry, strawberry, yes, strawberry, strawberry, or chocolate, vanilla, vanilla, strawberry, vanilla, vanilla, or vanilla, strawberry, strawberry. And finally, we can have all three flavors, and we'll have two columns of that, chocolate, vanilla, strawberry, strawberry, chocolate, vanilla, vanilla, chocolate, strawberry, vanilla, strawberry, vanilla, chocolate, or vanilla, strawberry, chocolate. Now, it's kind of a pain listing all those out. You know, if we had more flavors or more scoops, this would be virtually impossible. You get the idea of how you would group these all together, right? You're going to have to literally list out all the different types of cones. Yeah? And that should, in your mind, say, this is a real pain. There must be an easier way to calculate these combinations, yes? Yeah, so in the homework, you'll have a problem where you're given this table of scoops, and you have to go through it and say, well, which of these would still be around? Let's count up the number of possibilities if we're doing cones without repetition. So things like the first column here, chocolate, 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 vanilla, 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 strawberry, 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 would be out because that's all repeated flavors, yes? So those would be excluded. So you will go through the table and basically circle the combinations which will be allowed under the rule no repetition, and then count up how many there are manually just to do it once. And then the same thing for bowls, where order does not matter because the bowl doesn't matter what the order is. But we will, in general, rely on calculation techniques, formulas rather, to be able to calculate these number of combinations. And so that's what we're going to look at next. So let's restart the video. But what if we increase the options? Say 3 scoops and 4 flavors. That's when counting the number of ways becomes less intuitive and more complex. To tackle these more challenging scenarios, I'll introduce you to the formulas and methods that help compute these possibilities efficiently. Let's begin with the top left quadrant of our conceptual table, where order matters and repetition is allowed. In our first example, where repetition is allowed and order matters, we see a classic example of the application of the multiplication principle of combinatorics. Let's break it down with our simple ice cream scenario. Imagine you're choosing a 2-scoop ice cream cone from 2 available flavors. How many options do you have for the first scoop? 2. And for the second scoop? Well, still 2. Because repetition of flavors is permitted. So the total number of combinations for your cone is 2 times 2, which is 2 squared, which is 4. That's 4 different ways to build your ice cream cone. Now, what happens if we expand our options to 3 scoops and 3 flavors? You'd have 3 choices for each scoop, making the total combinations 3 times 3 times 3, which is just 3 cubed, which is equal to 27. 27 different ice cream cones. To generalize, if you have S scoops and F flavors, the total number of combinations is expressed as F raised to the power of S. For instance, a cone with 3 scoops from the 31 flavors at Baskin-Robbins could be arranged in 31 cubed ways, which is a total of 29,791 different combinations or different ice cream cones. It's a vast array, so you might think twice before trying one of each. Okay, so you see that that's the number of possibilities that we got when we considered the 3 scoops with 3 flavors in a cone. We got 1, 2, 3 times 1, 2, 3, 4, 5, 6, 7, 8, 9. And what is 9 times 3?
27.
27. But we could calculate it much easier using this formula or this technique where we laid out the scoops. And we said there are 3 possibilities for this scoop, chocolate, vanilla, or strawberry, 3 possibilities for this scoop, chocolate, vanilla, or strawberry, or 3 possibilities for this scoop. And that's the number of flavors is the number of possibilities is equal to the number of flavors raised to the number of scoops power, which is 27. So much easier to do. So the formula for calculating ice cream cones where order matters and repetition is allowed is just to simply take the number of flavors and raise it to the number of scoops that you're going to have. So let me give you one to try. How many cones can you make with 2 scoops and 4 flavors? So you don't have to draw out all the possibilities, you just need to calculate it. So go ahead and pause the video and do that now. Right, now you could have either used the formula directly from the counting matrix that I put up here, or you could calculate it manually like this. You could say, okay, I've got 2 scoops. There are my 2 scoops. My first scoop, I have 4 flavor possibilities. It would be chocolate, vanilla, strawberry, and pistachio, for example. But for my second scoop, since repetition is allowed, I have 4 choices for that one as well. And by the multiplication principle, the number of possibilities is 4 times 4, or 16. Or we could have used the formula from the counting matrix, which says take the number of flavors, which was 4, and raise it to the number of scoops power, which was 2. 4 squared is also 16. Make sense? Now, let me just emphasize that this doesn't only apply to ice cream problems. So consider the following. Okay, you find yourself abducted by an alien species and taken back to their home planet. And before they introduce you into their society, they give you a test to take. It's a multiple choice test with each question having choices A, B, or C. But you don't read their alien language, so it looks like gobbledygook to you. So how many possible answers are there to this test? And how is this like an ice cream problem? Think of the number of questions as the number of scoops, and the number of choices as the number of flavors. So think of it as an ice cream. So for the first scoop, you could have flavor A, B, or C. For the second scoop, flavor A, B, or C. So think of it like that and see if you can calculate the number of possible test results for this alien test. So pause the video, try that now. Well, if we write this down and say, all right, well, question 1 has, let's do it like this. Question 1, question 2, question 3, and question 4. Those are my 4 scoops. How many choices do I have for question 1? I have 3 choices. How many choices do I have for question 2? Also 3 choices. And the same goes for question 3 and question 4. And by the multiplication principle, the answer should be 3 times 3, which is 9, times 3, which is 27, times 3, which is 81. Or we could have used our formula from the counting matrix and said that the number of possibilities is equal to, well, if flavors is questions, that's 3 flavors, A, B, or C, and scoops is the number of questions, or 4, so 3 to the 4, which is also 81. Make sense? Okay. So if you remember anything, try to remember this technique of allocating out the scoops or the placeholders, and then asking yourself, how many choices do I have for each one? So if you can find a counting problem and put it into that format, then you can usually answer it pretty easily, rather than simply relying on formulas, and certainly easier than delineating all the different possibilities, because you don't want to write out all the 81 possible answers, right? You know, it could be one choice could be A, C, C, A. That's one of the 81 possibilities, and you don't want to have to list the other 80, right? So counting them up either like this or using the formula is much faster, much easier. Let's continue the video. In the previous scenario, we always had the same number of choices for each scoop. However, when repetition is not allowed and order matters, each subsequent choice becomes increasingly limited. For example, if the first scoop has 2 flavor options, like chocolate or vanilla, selecting one reduces the choices for the second scoop to just 1 remaining flavor. Let's illustrate this with our 2-scoop, 2-flavor example from earlier in the video. If we choose chocolate first, then vanilla is the only option left for the second scoop. And if we choose vanilla first, then the second scoop has to be chocolate, resulting in 2 choices for the first scoop and 1 choice for the second scoop. 2 times 1 equals 2 choices, or 2 unique combinations. Now, what if the options are expanded to 3 flavors, but we stay limited to just 2 scoops? The first scoop gives us 3 choices. After choosing one, only 2 flavors remain for the second scoop, giving us 2 choices, followed by 1 choice for the final scoop. That gives us 3 times 2 times 1 equals 6 possible cones. This kind of sequential reduction in choices is captured mathematically by what's known as a factorial. For 3 flavors and 2 scoops, it's calculated as 3 factorial equals 3 times 2 times 1 equals 6. This factorial concept becomes even more interesting with more flavors. For instance, if 4 flavors are available, but we can only choose 2 scoops, the calculation would be 4 choices for the first scoop and 3 choices for the second, resulting in 4 times 3 equals 12 unique combinations. However, if we were choosing all 4 flavors in sequence, the factorial of 4 equals 24 different combinations, 4 times 3 times 2 times 1. In terms of formulas, with F representing flavors and S representing scoops, just as before, the number of ways to assemble the ice cream is given by F factorial divided by F minus S factorial. The division is simply removing from the count the choices we would have if we had as many scoops as flavors. So we first compute as if we had as many scoops as flavors, and then divide by the complementary factorial to restrict the number of scoops. So for example, here, we would have 4 factorial divided by 4 minus 2 is 2 factorial. That's 4 times 3 times 2 times 1 divided by 2 times 1. 1 and the 2's cancel, and we're just left with 4 times 3 equals 12. Let's return to Baskin-Robbins and imagine that they have restricted us to no repeat flavors on a 3-scoop cone. The combinations possible plummet from a staggering 31 cubed, which was equal to 29,791 from the exponential case, to a factorial-based calculation of 31 factorial divided by 31 minus 3 factorial, which is equal to 31 times 30 times 29. Since 31 minus 3 is 28, we're going to divide by 28 factorial. So we can cancel everything out from here. And so we get 31 times 30 times 29. And what's that equal to? That's equal to 26,970 different combinations. Still, quite a hefty number of flavor permutations. Okay, so the factorial is definitely a new concept to us. It's a little bit like an exponent, right? Like 2 cubed or 2 to the 4th or 2 to the 5th. It grows very fast, actually grows faster at some point. But the idea is relatively simple. If I write 5 factorial, it just means 5 times 4 times 3 times 2 times 1. But working with factorials, there are some tricks. So I've written an expression up here, 14 factorial divided by 4 factorial times 3 factorial times 8 factorial. And I think it's worthwhile to spend a minute and go through it and see how we'd solve this easily. So the first thing we want to do, we want to take advantage of the key fraction rule and get cancellation. Okay, so we see that our biggest factorial in the denominator is 8 factorial. So I want to write out 14 factorial up to the point where I get to 8 factorial and then stop. So I'll write it like this. 14 times 13 times 12 times 11 times 10 times 9. And instead of writing times 8 times 7, I'm going to write times 8 factorial. So that just means I continue counting down. 8 times 7 times 6 times 5, right? Because we're going to cancel that with the 8 factorial that is in the denominator here. So those go away. And so I'm just left with 14 times 13 times 12 times 11 times 10 times 9 in the numerator. But I still have in the denominator, I have 4 factorial times 3 factorial. And here it's probably worthwhile to reduce things. So 3 factorial, that's 3 times 2 times 1. The 1 is inconsequential, but 3 times 2 is 6. So I can erase 3 factorial, replace it with 6, and use it to cancel whatever's convenient up in the numerator. So I see the factor of 12 up here, right? That's 6 times 2, correct? Yeah. So I can cancel out this 6 with this 12, leaving a 2 behind. Because 12 divided by 6 is 2. Does that make sense? Do you see what I'm doing here? Yes. Did a lot of this kind of stuff when we did fractions. We still have the 4 factorial. Maybe I shouldn't have done that cancellation, actually. Yeah, I think I changed my mind. I don't want to cancel the 12, so I'll put the 12 back. And instead, the 6 I'm going to use to cancel partially with the 9. So I'm going to write this as 3 times 2, because 9 divided by 3 is 3. 4 factorial is 4 times 3 times 2, times 1, of course, but that's, again, inconsequential. But 4 times 3 is 12. So this is 12 times 2. So 12 times 2 the 12 will cancel perfectly with that 12. And so I have a 2 and a 2. So I need to factor that out up here somewhere. The 14, if I factor out a 2 of that, I'll be left with 7. And the 10, if I factor out a 2 out of that, I'll be left with 5. And so what do I have? I have 7 times 13 times 11 times 5 times 3. I think that's all I have left. So let's do the easiest things first. I don't know if you guys know the rule for quickly multiplying by 11. So if I want to do 13 times 11, the answer is going to be 1 because of the 1 in front of the 13. And then 1 plus 3 is 4. And then it'll end in 3. So 143. Okay, it's a fast way to multiply by 11. So I have 143, and then I still have the 7, 5, and 3. So I think what I'd like to do is maybe do the 5 times 3, which is going to give me 15. And then I can do 7 times 15. Well, that's going to be 7 times 5. I'm going to write it as 10 plus 5. That's 15, right? 7 times 10 is 70. And 7 times 5 is 35. So this is going to give me 70 plus 35. And since 70 plus 30 is exactly 100, this reduces to just 143 times 105. But 105 we can write more easily as 100 plus 5. Yeah? Yeah. And 143 times 100, we're just going to add 2 zeros to it. So that's going to give me 14300. Or 14,300. And then 143 times 5, that's also relatively easy because it's half of 1,430. So half of 14 is 7, and half of 30 is 15. So I have 14,300 plus 715. Well, again, 7 and 3, that's a perfect, makes 10. So that's going to give me 15,015 is what I had left over there. And so 14 factorial divided by 4 factorial times 3 factorial times 8 factorial is equal to 15,015. Okay. So that is, if you are comfortable working with factorials in this fashion, then using them in the counting problems, will be much easier. That said, let's look at an actual counting problem. Maybe I should give you one of these common factorial problems to try at home. What is 6 factorial divided by 5 factorial? This should be a fast one. Pause the video, come back when you have your answer. Does anyone want to take a wild guess at what the answer is?
6.
6, right? Because we can rewrite this as 6 times 5 factorial divided by 5 factorial. The 5 factorials cancel, I'm just left with 6. Isn't that nice? Okay, let's do some counting problems. Not ice cream problems, though, because again, I want you to be able to apply the techniques using the ice cream analogy, though, to real counting problems. So first problem, how many different 5-digit zip codes are there? How would we figure that out? 5-digit zip codes. Well, you should start with the 5 digits. Think of that like the scoops. So I've got 5 digits I've got to fill in. 1, 2, 3, 4, 5. How many choices do I have for the first digit? I mean, a zip code, that's in numbers, right?
You got 9 choices.
9?
10.
I have 10 choices, right? I'm going to assume that it's okay to start zip codes with 0. I think it is. I think I've heard zip codes that begin with 0, but I'm not 100% on that. But yeah, we have 10 choices. And how many choices do we have for the second digit of the zip code? Also 10. Also 10, also 10, also 10. So this, in the end, the number, we would just multiply each of these through the multiplication principle, and the number would turn out to be 10 to the 5th, or 100,000 different zip codes. Now let me give you one to try. So I would like you to answer the question, how many zip codes are there with no repeated digits? So for example, my zip code begins with 77. That's a repeated digit. We're looking for zip codes that don't have repetition at all. So pause the video, try that now at home, come back when you have your answer. Well, let's begin like we did here. Let's write down our scoops, or our zip code digit positions. And how many choices do we have for this first digit in the zip code? 10. Yeah. But let's think about, let's put all the digits up here. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? There are 10 digits that can be in the zip code. And we've chosen one of them. Let's just randomly say that we chose this 7. So that 7 is out of the mix. There's no repetition, so I cannot use it in the next digit, yes? So how many choices do I have for this next digit? Well, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? I have 9 choices. So I'll put the 9 in here. That, of course, means that we've used another number. Let's just say we used the 4, so that's out of the mix now. How many choices do we have for the next digit? 8. And for the next digit?
7.
And for the next digit? 6. So this is 10 times 9 times 8 times 7 times 6. Okay?
Yeah.
But you can write it. You want to write it in factorial fashion. How would you do that? You would write it like this. You'd write it as 10 factorial divided by, well, what would we be dividing out here? Well, we've got 10 times 9 times 8 times 7 times 6. We're missing the times 5 factorial, right? So divided by 5 factorial. Okay? And I'll let you multiply those out at home. I'm sure that'll be a fun exercise. But if you're looking for the right answer, you'll get 30,240. But let's return to the video again. Flavor permutations. Before moving on to the ice cream bowls section of our table, let's talk about the number of ways a word can be rearranged. How many 3-letter words can you make from the letters T, O, and M? And no, they don't all have to be real words, like Tom. They can be nonsense words like MTO. The best way to solve a problem like this is systematically. We will order our letters from lowest to highest. M, followed by O, followed by T. Next, we will imagine 3 blanks. These are the first, second, and third letters for our proposed word. How many choices do we have for the first slot? We can choose the M, the O, or the T. So 3 choices. Let's assume we pick T. For the next slot, we only have 2 choices, the O and the M. So let's pick O. I guess you know where I'm going with this. For the last slot, there's only 1 letter choice remaining, the M. By the multiplication principle of combinatorics, that is 3 times 2 times 1 equals 6 possible words. What are these words? Let me show you a systematic way to arrive at all the possibilities using a tree diagram. Start by spacing all 3 letters out vertically as follows. M, O, T. Starting at the top, construct 2 branches adjacent to each of the 3 letters. Why 2 branches? Because there are 3 minus 1 letters left. Now fill in each of the 2 branches with the 2 letters not yet listed in each row. Next, draw a single branch next to each letter and add the 1 letter missing from that row or path. Finally, write all the letters in the path to get all 6 words. If we think of this word rearrangement problem like we did about ice cream cones, where instead of scoops we have slots for letters, then we can recover the same factorial equation we saw for scoops of ice cream in a cone. Similarly, if we have more letters to use than slots to put them in, then we can use the full formula of number of ways equals f factorial over f minus s factorial, where instead of flavors, we will use number of distinct letters, and instead of scoops, we will use word length. What happens if we have repeated letters, like in the word Bob? Let's make another tree diagram, but let's temporarily distinguish between the 2 B's. I'll make one an uppercase B and the other a lowercase. We can use the same tree diagram from before, where the T is replaced by the uppercase B, and the M is replaced by a lowercase b. Since there is no difference between the 2 B's, half of these words are duplicates, and so the simple factorial formula we used before overcounts. But by how much? We need to divide by the number of ways to permute uppercase B and lowercase b, so 2 factorial. Thus we divide the count from before by 2, which is why we saw half the words as duplicates. Let's apply this to a more complicated word with a lot of repeated letters. Mississippi is a long word with 4 repeated S's, 4 repeated I's, and 2 repeated P's. This word has 11 letters, so we start with 11 factorial. This, however, overcounts, so we divide out 4 factorial for the repeated S's, and another 4 factorial for the repeated I's, and finally 2 factorial for the repeated P's. So the number of ways is given by I will leave it to you to check that this is correct. So get out your Scrabble boards and start arranging. Okay, so that probably made a lot of sense given our zip code problem that we started with. And I'll point out, right, that to apply the formula here to the zip code problem, we had 10 factorial would be the number of flavors, divided by 10 minus the number of scoops. Number of scoops would be the digits, or 5 digits. So 10 minus 5 is 5 factorial, or 10 minus 5 is 5, and so we'd have 10 factorial divided by 5 factorial, and that would be the same as what we calculated manually using the multiplication principle in the problem, okay? But let's apply the techniques that we saw in the video about calculating the number of ways to rearrange a word. So here we have the word Tennessee, a lot of repeated letters in it. So try to apply the techniques that you saw in the video to the word Tennessee. Pause the video, come back when you have your answer. Well, what is the word length? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So we know we're going to have a 9 factorial in the numerator. What about the denominator? That's where we put the repeated letters. So we have no repeated T's. We have 1, 2, 3, 4 repeated E's. So we need to divide that by 4 factorial. We also have 1, 2 repeated N's. So divide by 2 factorial. And then 2 repeated S's, another 2 factorial. And so you see, we can use the techniques that we learned about dealing with these factorial ratios. And we'll write this out as 9 times 8 times 7 times 6 times 5 times 4 factorial. So we turn 9 factorial into this expression. And we did that because we have a 4 factorial in the denominator, which we will cancel out with the key fraction rule. And we're still left with 2 factorial times 2 factorial, but that's just 4. So we think of it as 2 times 2. And we can take 1 2 from this 6, making it a 3. And we can take another 2 from this 8, making it a 4. And so we're left with 9 times 4 times 3 times 5. And what order would you like to try it in? Would someone like to pick an order? Would you like to do 9 times 4 is 36? Start with that, or would you rather start with 9 times 5 is 45? Any choices? You want to do 9 times 4 is 36? Let's just write it down. So we've got 36 times 3 times 5. Well, the 36 times 3, we're going to get 90 plus 18. That's going to be 108 times 5. So what is 108 times 5? That's half of 1,080. So that would be 540. So we should get 540 as our answer. But that's not right, is it? Oh, I think I realized where we messed up. We're missing the 7, right? Yeah, we're missing the 7, right? So we still need to add in times 7. So 540 times 7, what are we going to get? 7 times 4 is 28. 7 times 5 is 35 plus 2. So we should get 3780. Yes, that's right. 3780 is our final answer. So you've got to be careful and don't forget about one of the factors up there when multiplying it all through. So I should put that in here as well, huh? Times the 7, times the 7, times the 7. So let's go back to the video now. Start arranging. What use is this for our ice cream problems? Well, in order to answer that, I must first tell you about committee problems. Okay, how many ways can we form a student committee of 2 students from a class of 5? Well, start with the 5 students. Then add 2 O's for the 2 people on the committee. Doesn't matter which we choose, so we may as well choose the first 2. Next, add an X underneath each member of the rest of the class to designate them as not on the committee. I leave it to you to prove to yourself that the committee question is the same as asking how many ways we can rearrange the word ooks. We know how to answer this. It's just 5 factorial divided by 2 factorial. The 2 factorial is for the O's, and we also need a 3 factorial for the X's. So the number of rearrangements and the number of possible committees is then, well, this will just reduce to 5 times 2, or 10 possible committees. In combinatorics, these committee problems are called in choose K. It's usually written like this, in choose K. Our problem was 5 choose 2. We write in choose K, the formula for it anyways, is written like this. In choose K is equal to in factorial divided by k factorial, all times n minus k factorial. So simply substitute n equals 5 and k equals 2 in the formula, and voila. Okay, so n choose k, which is written like this, and you don't have to worry about it, to be honest, because we don't really need it. Okay, if you think about it as a word rearrangement problem, you don't have to rely on using this factorial formula. Instead, we can look at it as just a simple word rearrangement problem. So I'm going to do n choose k on a problem like this. So in a squad of 9 soldiers, how many 4-person fire teams can you form? This is just a committee problem. So you can solve it using the n choose k formula, or you can set up the kind of word problem that we saw in the video a moment ago. So go ahead and pause the video, try that now, come back when you have your answer. So what I'd like to do is just simply draw in the 9 soldiers. There's 1, there's 2, we don't have to give them guns. That would be cumbersome. I've got 5, there's 6, 7, 8, and 9. So here are our 9 soldiers. Let's label who's on the fire team with an O and who's not on the fire team with an X. And so we'll just start with the first possibility of putting the first 4 people we see on the fire team and everyone else is not. And so now our combinatorics problem, which we could solve using n choose k formula, but we can solve it more easily just by using this word rearrangement problem. We've got the word ooks that we need to rearrange. And so how do we solve that? Well, how many digits are there? What's the word length? It's 9 soldiers, so it's a 9-digit word. So that's 9 factorial divided by any repetitions that we have. Well, we've got 4 repeated O's, and we've got 5 repeated X's. So again, we see we've got a 5 factorial in the denominator, so we'll go ahead and expand 9 factorial to be 9 times 8 times 7 times 6 times 5 factorial, because we'll divide by 5 factorial, which will cancel that. But we still have the 4 factorial, which is 4 times 3 times 2. And so we'll just look for places to get these cancellations from. So the 3 times 2, well, that's really 6, right? So this whole thing here will cancel that 6 out. And then we've got the 4, which we can cancel part of 8 out with, leaving us with just 2. And so we've got 9 times 2. Let's try not to leave any factors out like that 7. I think we got it all. Yeah, 9 times 2 times 7. Well, what is 9 times 7?
63.
63. So 63 times 2 would be 126. So we have 126 different possible fire teams that we can form from 9 soldiers. So let's continue the video at this point, and voila. Okay, let's dive back into our ice cream exploration. Consider this. How many different 2-scoop ice cream bowls can you create from 2 flavors when no flavor is repeated? Since the order in a bowl doesn't matter, that might seem like a simple question because there's obviously only one possible combination. Let's check if our formula holds up. With 2 choices and no repetitions, our calculation is 2 factorial divided by 2 factorial times 0 factorial. Interestingly, 0 factorial is defined as 1. Surprising. But it's a standard mathematical convention, and you'll just have to trust me on that. According to this formula, we indeed end up with 1 unique bowl. I don't think, however, that we've really showcased this method well, so let's return to Baskin-Robbins. How many unique flavored 3-scoop bowls can we concoct from their array of 31 flavors? Applying our formula, we calculate it as 31 choose 3, which is 31 factorial divided by product of 3 factorial and 28 factorial. Simplifying this, we get 31 times 30 times 29 divided by 6, which equates to 31 times 29 times 5. What do we get then? Doing the math, that's 155 times 29, which is equal to 4,495. While still a large number, it's significantly fewer than the 26,970 unique flavored ice cream cones or the staggering 29,791 unrestricted cones we discussed earlier. And with that, we're almost entirely through our ice cream scenario table. Okay, so we can now fill in this lower right quadrant. The method to deal with ice cream bowls where repetition is not allowed, these are the subsets, is to use F choose S, where F is flavors, S is scoops. So let's put it to practice and try a problem. Okay, how many different bowls can you make with 4 different scoops and 5 flavors. Different is the important operative word here. 4 scoops would indicate or imply that repetition is allowed. 4 different scoops, that means that repetition is not allowed. Okay? So you have to pay careful attention to the wording in counting problems to try to understand whether order matters or whether repetition is allowed. So go ahead and try that at home. You can either use the formula or you can construct it manually using the principles we talked about before by word rearrangement. Pause the video, come back when you have your answer. So here's what we could do to set this problem up. We've got 5 different flavors. So let's put our flavors down. We could have chocolate, vanilla, strawberry, pistachio. We need one more flavor. Anybody have a favorite?
Cookies and cream.
Cookies and cream, okay. We'll call that CC, even though that's, well, I'll put commas here so we see that they're all different. So there are 5 flavors of ice cream. Let's just make a word problem out of it. So we're going to put some of these guys in the bowl and some of them not in the bowl, right? So we'll put chocolate in the bowl, vanilla in the bowl, strawberries in the bowl, pistachios in the bowl, but cookies and cream is out of the bowl. That's one possible committee that we can form from this, yes? But that's a word, ooks, or really, ooks, right? So what are the number of ways to rearrange that word? Well, there are 1, 2, 3, 4, 5 letters in that word. So it's a word of length 5. So we have 5 factorial divided by any repetition that we see. Well, we've got 4 O's, so 4 factorial, and then 1 X. We could write 1 factorial, but 1 factorial is just 1. And I don't know if I mentioned, but so is 0 factorial. So if you run into 0 factorial, it is by definition 1. So 5 factorial divided by 4 factorial is just 5. So there are 5 bowls that you can make. Okay. Now you could have used the formula. Flavors was 5. Scoops was 4. And that would be 5 factorial divided by 4 factorial times 5 minus 4 factorial, which in the end just gives you 5. Your choice. I prefer to do it like this. That way you don't have to memorize formulas and stuff, because you can mess them up. You can forget the formula and use it incorrectly. But if you get the methodology down, the word rearrangement methodology, then you'll have no problems. It can even be more robust than that, but I'm not going to go into the details on that. But it's a very good way to enumerate these counting problems. Okay, let's go ahead and resume the video. When order does not matter and repetition is allowed, we adopt a clever labeling scheme known as stars and bars. Although I'm not certain of its origin, the earliest usage I know of is from Paul Ehrenfest in 1914, who used this technique to derive Max Planck's formula for distributing energy among single-frequency resonators. Let's apply this to the last quadrant in our table, unrestricted 2-scoop ice cream bowls. We use an O to represent a scoop of ice cream and a vertical bar as the partition between flavors. In this system, only one partition is needed. If the O is to the left of the partition, it represents a vanilla scoop. To the right, it represents a chocolate scoop. For example, 2 chocolate scoops would be represented as a partition followed by OO, and one of each flavor as O partition O. If we label the vertical partition as L, we could describe the 2 chocolate scoops as Lu, and 1 scoop as the word Olo. The number of ways to arrange 2 unrestricted scoops from 2 flavors can be equated to rearranging the letters in Olo. With 3 positions and 2 repeating elements, this calculates to 3 factorial divided by 2 factorial, which is equal to 3 different combinations, matching our earlier result. All right, one final visit to Baskin-Robbins. If we scale this up to a more complex scenario with 3 unrestricted scoops from 31 flavors, we face a new challenge. The configuration could be represented as a sequence with 3 O's and 30 L's, indicating scoops and partitions respectively. The mathematical challenge then becomes calculating the permutations of OOLOL, which is 31 factorial divided by 30 factorial and 3 factorial. And that is equal to 11 times 16 times 31, which equals 5,456 possible combinations. I think that is still too much to try every combination. Let's summarize the methods described here as it relates to our table. Okay, stars and bars is a great technique. If you ever come across how many ways can you arrange, C distinct candies into, or C identical candies into B distinct bags, then stars and bars is your friend. It's going to help you out. But let's try and apply it to an ice cream problem. So imagine that we had the following four flavor possibility. We had chocolate or vanilla or strawberry or pistachio. And we want to make an ice cream bowl where repetition is allowed. So it's a word problem, but we're going to do it using stars and bars. So I've already created the partitions for you to know where you put the stars in order to make the flavored scoops. So let's write the question. How many? Oh, sorry. I wanted to make it 3 scoops. So how many bowls can you make with 3 scoops and 4 flavors? So notice that there's not different scoops there, so that means that repetition is allowed. They could all 3 be chocolate if that's what you preferred. So pause the video, try that now, come back when you have your answer. Well, again, just configure one bowl. So we'll make 3 scoops of chocolate, but we have to put in our partitions. 1, 2, 3 partitions, right? If they're all the way to the left, that's the chocolate. If they're here between the first and the second partition, that's the vanilla. If they're between the second and third partition, that's the strawberry. And if they're after the third partition, that's the pistachio. So I put my 3 scoops in the chocolate area. And I can now calculate this word because it's got 1, 2, 3, 4, 5, 6 letters in it. So it's 6 factorial divided by the repetitions. I've got 3 factorial from the O's and 3 factorials from the L's. Yes? So we can rewrite this as 6 times 5 times 4 times 3 factorial, which will divide out a 3 factorial here. But we still have another 3 factorial, which is 3 times 2 times 1, which is just 6. So that 6 will cancel out here, and I'm left with 5 times 4, which is 20 possible bowls. Yeah. All right, so let's just watch the summary from the video. But let me just put up here that we're going to insert into our table. I don't really know a good way to write stars and bars shorthand, but I'll just write this. O-O-L-L-L for the problem that we just did. So if you're in this quadrant, if you're looking at bowls that allow repetition, then you want to use stars and bars. If you're in the bottom right quadrant, it's the committee problem, or N choose K, but I wrote it as F choose S for flavors and scoops. There's just not a really convenient way to write that here. Okay, so I just put the general stars and bars symbol. Let's watch the summary. In the upper left quadrant, dealing with counting problems where order matters and repetition is allowed, the number of ways is given by an exponential. For our ice cream example, the number of possible unrestricted flavor combinations, S scoop cones from F flavors, is given by F raised to the S power. In the lower left quadrant, in which order matters but repetition is not allowed, the number of ways is given by a factorial. For our ice cream example, the number of possible unique flavored S scoop cones from F flavors is given by F factorial divided by F minus S factorial. The rightmost quadrants can be calculated using a labeling scheme applied to a word rearrangement problem. The upper right quadrant, where order doesn't matter and repetition is allowed, uses stars and bars for calculation. The lower right quadrant, where order doesn't matter and repetition is not allowed, uses the method of X's and O's, or N choose K. You won't be able to crack every counting problem that you might encounter with these methods, but it is a good start. I hope you have enjoyed this intriguing journey through the world of combinatorics, exploring how simple principles can unravel complex counting challenges. Remember, this is just the tip of the iceberg when it comes to the power of combinatorics. Don't forget to like, subscribe, and click the notification bell so you don't miss my future explorations of mathematical and physics concepts. And remember, stay curious. Does anyone want some ice cream? Okay, makes me wish I had some ice cream, and I'll put a link to the original video on Prodigy physics in the description of this video. But I want to end by talking about divisors and how many possible divisors that you can get. So let's imagine that we have a composite number And I'll just use a real number. Let's say 210. And if you draw a factor tree for 210, you're going to find that it factors as 2 times 3 times 5 times 7. It's a good starting digit if you like to play numble. That's my game. I'll also put a link in the description to that. So 2 times 3 times 5 times 7. How many possible divisors are there? I know you're going to probably say, oh, well, it looks like there's 4, right? But what I mean is, for example, 2 times 3 is 6. That's a divisor of 210. So we don't know how many possible divisors there are. So you can think of it kind of like how many 1, 2, 3, or 4 scoop ice cream bowls are there? Because those are the possibilities for the divisors. So what is a 1 scoop? That we call a 1 scoop would be just a single factor. And that's pretty easy, right? So we write down all the factors, 2, 3, 5, 7. Single factor in it means we put an O here, and everybody else gets an X. So this becomes the problem of 4 factorial divided by 3 factorial, which equals 4. So there are 4 possible single factors. You probably see them because they're staring at you. It's 2, 3, 5, and 7. There's actually another one that I haven't included, and that's 1. That's another factor that we would have to throw in there. What about 2 scoop, right? Or 2 flavor scoops. We call these 2 factor, or I guess no, 2 scoop ice cream bowls is the way to say it. 2 scoop ice cream bowls. For that, we just write it out like this, 2, 3, 5, and 7. Now we get 2 scoops. So we have 2 people on the committee, if you want to think of it that way. And these guys are off the committee. How many different ways can we arrange that? Well, the number is equal to, again, 4 factorial divided by 2 factorial times 2 factorial. So that's going to be 4 times 3 divided by 2, which is just 2 times 3, which is just 6. So there are 6 possible 2-factor divisors. 2 times 3 is 6 is one of them. Another one would be 2 times 7 is 14. That's another 2-factor divisor. We can also have 3-factor divisors, or 3 scoop ice cream bowls. And so we do it the same way for 2 times 3 times 5 times 7. We have O, O, and O. We've got 3 factors in there. So the number of divisors in this case will be 4 factorial divided by 3 factorial times 1 factorial. So this is just 4. And finally, we've got our 4 scoop ice cream bowls that we can make. 2, 3, 5, and 7 are the factors, and they're all in there. So that's just going to be equal to 4 factorial over 4 factorial, which is just 1. And then you can think of a 0-factor ice cream bowl, right? That would be the one that included the 1. So now we want to add up all of these different things, right? The number of divisors is just the sum of these. So we have 4 plus 6 plus 4 plus 1 plus the other one, right? The one for 0 factors, or. So what do we get when we add that up? Well, 6 plus 4 is 10, and plus another 4 is 14, plus 1 is 15, plus another 1 is 16. So we get 16 divisors. Now the question is, was there an easier way to calculate this other than going through each of the different combinations? And the answer is yes, there is. Another way to look at it is we can write down the different factors, 2, 3, 5, and 7, and either it's in the divisor or it's not in the divisor. So how many different ways? Think of these as like slots. It's either in the divisor or it's not in the divisor. So that's 2 choices, yes or no. So we have 2 times 2 times 2 times 2, which is 2 to the 4th power, which is 16. So we could have calculated this directly. Now that was pretty easy because we didn't have any repeated factors. A lot of things have repeated factors. So for example, the number 8 is written as 2 times 2 times 2, or 2 cubed. But I want to look at a problem that has a mixture of repeated and non-repeated factors. So let's look at 12, which is 2 times 2 times 3. That's 4 times 3, right? 12. So here the 2 is repeated, but the 3 is not. So how do we enumerate this? Well, we can think of, well, really we've just got 2 slots, right? One for the 2, one for the 3. But for 2, it has 3 actual choices. It can be in the divisor, it can not be in the divisor, or it can be in the divisor twice. So that's 3 choices for the 2. And the 3 only has 1 choice. It's either in there or it's not in there, so that's a 2. So the number of ways, or the number of divisors in 12 with the repeated digit is is 6. If you had thought of it as 1, 2, 3, 2 cubed, that would have been 8. You'd have overcounted. So I understand this can be tricky, and my advice is, the methods that we use to derive this counting matrix up here, use those methods of coming up with some bins and counting the number of ways and just using the multiplication principle, and you can solve most counting problems. Not all. There are a lot of counting problems that I did not include here. If you want a complete list, this is like four methods. There are actually 12 general methods to solve, I think, all the counting problems. We call it the 12-fold path, I think. But this will get you a long ways. And counting can be fun, but it is hard because it requires that you think about it. It's not something that you can just do by memorizing the procedure. You really have to think in order to solve these difficult counting problems. How many different ways can you do this or that? But it's very useful. It's especially useful in probability, where you need to know how many possibilities there are for something in order to figure out your odds of getting it or not getting it, right? And we'll talk about probability in the next lecture. So I'll see you then.